In the previous class, we started looking at this sessile droplet, and we showed that, for example, that flow in sessile droplet is created due to evaporation, or rather due to the asymmetry of evaporation. That means the droplet tends to vaporize more near the three-phase contact line than at the apex. So based on that, we formulated that following Deegan, that how that such a flow can be understood and how that evaporation phenomena can be understood as well. In this particular thing, we look at the simple, for example, the same droplet, where you can see here the maximum evaporation flux comes from the three-phase contact line, which we already said, and that is what creates that capillary flow. So the evaporation flux, however, here there is nothing convective about it, as we know. So this is a pure diffusion equation, right. So this is diffusion in equation in nature, where Cs is basically the vapor layer that surrounds the droplet surface, and C infinity is the concentration of the same vapor in the far infinity, A being the surface area of the droplet and R being the contact radius. So, and D is basically the water vapor air diffusion coefficient. If instead of water droplet this is something else, say for example it is say ethanol, or it is something of that kind, then of course you will have a very different diffusion coefficient. Okay. So that value is dependent on the application that you are dealing with, right. So that is the J. Okay. So Popov, what he did was that he gave another expression in terms of the contact angle now, but as we said that when the droplet evaporates, if you remember, there is something called CCR, CCA and mixed mode that we already did in the last class. So Popov did was that he gave the following expression for the contact angle. So that means what he did was he basically cast J, which is basically the rate of change of volume of the droplet. It was written once again in terms of D and the concentration difference. In addition, there is an F theta parameter, where F theta for low contact angle is given in this particular form. For high contact angle, okay, it is given in that particular form. Okay. So where m is once again the molecular weight of water, rho is the density and v is the droplet volume. So if you just plot this kind of a volume flux with time, you will find that this is the kind of trajectory that the droplet follows for all volumes. These are of different volumes, so their starting points are obviously different, but they show almost like this kind of a linear regression with kind of time, except towards the end where you start to see the change in the slope. And if you look at the time history of the droplet, it looks precisely something like this. Okay. So in this particular experiment, for example, you can see that the contact angle perhaps remains almost very similar in all the cases if you look across the board. Okay. So these two expressions are important. So this was given by Popov, and there are varieties of other improvements on this equation, and this is the standard diffusion equation that is not based on any assumption, but just based on that only it is a diffusion driven problem. Now in case, so we will come to that in a second. So in order to calculate the droplet volume, for example, usually what we take is a spherical cap assumption. That means the droplet is like a cap. Okay. So it is like a part of a sphere basically. So this is how the spherical cap is given, and it is applicable for any contact angle droplets as a matter of fact. Okay. Now if the droplet is sitting on a platform like this, so far we have seen that it is basically what we call a diffusion problem. That means the water vapor accumulates here and then it diffuses out to the infinity just because of the concentration gradient. However, if there is a flow, that means there is a convective flow that happens. So what that flow will do is that it will go over the droplet, right. So it will basically dislodge this saturation water vapor that is accumulating near the droplet surface. So actually fresh stock of air would be brought in, As a result of that, you can expect an increase in the J flux. That is because simply you are not bound by diffusion anymore. There is actually a velocity which is carrying a parcel of this vapor that is evaporated to the far field, and the process is still happening in the same way. That means the droplet is still vaporizing in a quasi steady kind of a fashion. There is still an accumulation of CS very close to the surface, but this CS is basically now blown off to the far field. Okay. So basically you get an enhancement of J just because of the Reynolds number effect, and this will be particularly useful when you start looking at the scenario in the case of a contact free droplet, okay, where the effect is much more prominent. Okay. But the evaporation mechanism is the same, but the transport mechanism which determines the J, that is different. Okay. But it is still given by the Clausius-Clapeyron equation, that what is the vapor flux or the concentration of the water vapor or whatever vapor that you are dealing with it close to the surface. So far we have done it up to hydrophilic droplets. If you look at the case of droplets which are hydrophobic in nature, that means where the contact angle is like this. So it can be like, if you see the lotus leaf, you will find that the contact angles are much higher. So evaporation here is maximum in this particular plane rather than here. So it is a complete reversal. Okay. So if compared to a sessile droplet, what we had was that the evaporation was maximum here, sorry, and low in these zones. Here it is just the opposite, it is maximum here and it is the lowest at this particular point. So you get something like this. Okay. So now the reason is quite apparent. If you look at this particular situation, here you can see that it forms a wedge or basically a triangular region on both sides of the three phase contact line. So what happens is that if you just blow it up and see, you will see something like this. So this is the three phase contact line going up and this is the space. So as the water vapor leaks out, so you create this CS here. Now this water vapor now, because it is a diffusion driven problem, has to diffuse out from this wedge to the far field, so that more vapor can now evaporate and occupy this zone. Now because it is a wedge, so you can think of it that when you actually have a wedge anywhere in a system, it is very hard to basically pull out water vapor from that particular system, because you have that additional resistance, okay, of the constriction, which basically adds a layer of resistance for this water vapor or whatever vapor that you are dealing with to leak out and go to the ambient. Okay. So automatically what happens is that the vaporization rate is suppressed in this region, automatically that happens. So once again if you look at it, so if this is the wedge region, in this particular region there the evaporation will be suppressed, it is bound to happen. Whereas if you look at the curvature at the top, okay, you can see that it has got now the full free field basically to evaporate, right. So there is no problem now. So it can evaporate at whatever rate it wants, because there is no constriction, there is no wedge there. Now in the case of a hydrophilic droplets, it is like you can ask why it does not happen, because here it is an open wedge. Okay. So it is an open cavity, here it is a closed cavity. So that is the reason you have more accumulation of water vapor here and there is no accumulation there. So that is why you have a reversal of the J. Okay. So J is higher here and lower there, opposite to what you get in a hydrophilic sessile droplet, right. Now that creates one more thing. Now in this particular droplets you have seen that there is a flow field which is created because of the pinned contact line and to supply the solvent, because the evaporation flux is highest here. In this particular case, however, what happens is that because of suppression of evaporation here and an enhanced evaporation in this particular sector, okay, you create a small temperature difference. That means a small delta T. Okay. So that delta T what it does is that, okay, it results in higher evaporative cooling, okay, creating a temperature and hence a density gradient along the droplet height. Okay. So, the maximum evaporation from the top actually leads to a certain evaporative cooling at the top, right, whereas lower evaporation in this sector does not lead to the same extent of cooling, right. So, what happens is that you have naturally, okay, a density gradient that is created. So, the high temperature fluid basically starts to rise towards the top of the surface, and therefore, you get to see this kind of a recirculating flow that you see over here. This is in complete contrast to the flow that you would normally see in the hydrophilic case, right, because hydrophilic case you actually have a pinned line, and here the concentration is, the evaporation is the maximum. So, the flow straight away goes there. Here however, the flow, the evaporation is minimal here, maximal here. So, there is more evaporative cooling in this sector than in this sector. So, naturally the flow starts to rise in a buoyancy driven kind of a phenomena, right. Now, if these droplets also come with a little bit of surfactants, okay, or if the temperature difference is large enough that it can create what we call a surface tension gradient, right, you can see another type of flow that can happen, which is called Marangoni convection, right. So, that can also happen in these kind of cases. Okay. So, the flow that you see over here is buoyancy driven, is very feeble, because the temperature difference that you create for these kind of small droplets is really small. So, it is really small flow. Okay. But however, as we will see, if it is driven by Marangoni stress, that is due to the presence of surface tension gradient instead of density variation. So, the velocity field that is induced is given by, as you saw here, Vm. If that is the Marangoni velocity, it is d sigma by dt, that means there is a change in temperature which should bring about a change in surface tension, divided by delta t by mu. So, in essence, delta sigma by delta t is the rate of change of surface tension with temperature. This is the temperature difference, and this is the fluid viscosity. So, in this particular case, these velocities are normally very high, is normally high. So, Marangoni flow, or the flows which varies by surface tension, is actually given by this. So, what happens was that evaporation is still the driver, because of the wedge. So, if we recall the steps, because of the wedge there is a suppression of evaporation here. So, naturally that leads to a temperature gradient. So, there is a delta T that is created right away. Okay. Now, this delta T can either lead to a change in density, which can lead to a buoyancy driven flow, or it can lead to a change in the surface tension, giving rise to a Marangoni flow. So, it is the nature of the droplet geometry, right, the droplet geometry, and of course, there are parameters like thermal conductivity and things like that, which basically determines that the flow field that is subsequently created. So, in this case, though the evaporation phenomena is strictly driven by diffusion, right, the flow field that is inherently created within the droplet, that can happen due to Marangoni, or it can happen due to the buoyancy, due to the density. Okay. So, the same diffusion equations are valid for both the cases when you are computing J. Remember, we wrote it in terms of F theta, delta, surface tension, etc. So, that remains almost the same, except that you factor in the contact angle term. But apart from that, if you kind of try to understand the dynamics, that means the flow field that is created, the flow field is very different from that of a capillary, from that of a hydrophilic droplet. And this has got very wide implications, in the case of particle transport, whenever you are trying to do trying to custom engineer certain things in different applications, right, from biomedical applications, biomedical 3D printing, okay, then of course inkjet printing, okay, then of course you have surface patterning, big industry. Okay. So, lots of these things can actually lots of these things actually do involve calculation of J and the understanding of the internal flow field. So, we saw that J is kind of is a little immune of course, okay, but the flow field is not. Flow field is very different, and this changes with the change in the angle. That means you create a very hydrophobic droplet with a very sharp cavity or a wedge, okay, you will create more, the velocity of these flows will actually increase. Okay. So, those kind of things we have looked at it here. So, this is from the sessile framework. So, in the sessile framework we have only looked into the diffusion, and we have alluded that if there is a convective effect, what it will do is that it will enhance the evaporation rate just by blowing away the vapor field. Okay. And so, it is the same reason why you actually blow air over your tea or coffee. If it is very hot, what you do is that you blow air over it. That means normally if you allow it to evaporate normally, it is a diffusion driven problem. As soon as you blow, basically you are removing that saturated region of CS and you are replenishing it with a fresh stock of air, right. So, naturally the evaporation becomes a lot faster, right. So, so that can also, but when you actually blow air over the droplet, it can also influence the flow field inside, because you have to still maintain the integrity at the interface. That means that your boundary condition still has to match. Okay. So, there are different examples of different problems. For example, you can study similar such droplet under the under a convective field. I am not going to go into the details of these equations. There is a companion course which is also offered on NPTEL, which is called Heat Transfer and Combustion in Multiphase Systems, where we have mentioned all these things. So, basically it means that when you have two phases, you basically write the equations, the continuity equations for the two phases, and one for vapor and one for the liquid, and these are basically the mass added to from the liquid to the vapor, because it is an evaporating system, and vice versa. So, one will lose mass, one will gain mass, that is how it happens. Then you write the two momentum equations. So, this is basically a stream of droplets which are being flushed into a cooling tower type of an application, or a spray dryer in which an air is actually blown up. So, basically each droplet sees a flow field around it. Okay. So, here of course we are not concerned with each droplet, we are concerned with a global equation. Okay. So, this global equation, without going into the details, there are ways in which you can write volume averaged global equations, the details of which are not within the scope, but just to give you an idea. So, if you write the continuity equation, if you write the momentum equation, the liquid momentum equation, the vapor momentum equation, x and y both, you should be able to cast this problem and you should be able to solve it. So, this basically takes into account all the interface interactions that takes place between the two phases. Here once again we are not interested in one droplet, but these are thousands of droplets. So, we are more interested in a global volume averaged flow field and mass transfer and heat transfer issue. Okay. So, convection will actually increase the mass flux, it will increase because of the reasons that I cited already. It will also lead to change in the flow field because of the coupling that happens at the interface level. So, in the next lecture what we are going to look at, or immediately after this, is look at the problem of a contact free droplet to begin with. Okay. So, the contact free droplets are something that many of us have encountered, because one example is this spray dryer application that I just showed. So, if I take a box around it, I will see that there are thousands such droplets. So, we are interested in how each of these droplets behave. Okay. That is what we call a Lagrangian viewpoint, right. So, let us look into that. So, move to the next PPT. So, this is also droplet vaporization. So, let us look at the phenomenology first. Okay. So, the main idea of doing a droplet vaporization study is that if you look at this droplet over here, Okay. So, a single droplet basically exchanges heat, mass and momentum with its gaseous medium with the surrounding counterpart. So, here T infinity and Y1 infinity is basically the concentration or the mass fraction of whatever is evaporating in the far field. Okay. So, if it is a droplet of water evaporating here, it would be the concentration of the water vapor in the atmosphere in the far field much away from the droplet. So, what a droplet does is that it exchanges mass with this. So, if it is if it heats, it is called vaporization. If it condenses, it is called condensation. So, at the droplet surface, this Y1s is basically the saturation pressure of the vapor phase, okay, at the temperature of the droplet surface. So, if the droplet is here and if its surface temperature is say 320 Kelvin, right, then the Y1s will be whatever is the partial pressure of that particular vapor phase at 320 Kelvin. That means, it is essentially is the saturation vapor pressure at 320 Kelvin, right. So, that is what it says over here. So, in this case, when you have heat mass exchanges with the gas medium, so there are levels of complications that you can actually have. So, some people may be interested in a very detailed analysis, some people may be interested in just a heuristic type analysis. Okay. So, the complete analysis will involve basically 4 interacting processes, right. One is that we have to consider the liquid phase transport. So, if this is the droplet, what is happening within the droplet? So, that is your state 1, what is happening within the droplet. Okay. Then there is a gas phase transport, which is 2. So, gas phase transport is that what is happening in the gas phase, which is outside the droplet, right. So, the gas phase is the second one over here. Then phase change at the interface. So, this liquid is getting converted to vapor. So, there must be some phase change processes that must be happening at the interface. And in the case of reacting droplets, you can also have a reaction that is happening in this particular phase, especially say for combusting droplets, right. So, you have to solve 3 sets of systems basically with the coupling at the liquid gas interface in order to properly anchor this problem, right. So, the important considerations over here is the relative motion between the droplet and the gas phase, Stefan flow due to surface gasification, there is droplet drag and internal recirculation within the droplet. You will not understand many of these things ad hoc. Okay. So, first and foremost, let us try to put a little bit of a context to it. So, when a droplet is actually injected, these droplets are usually in a flow field, like for example, that spray dryer application that or cooling tower application that I showed. So, these droplets has got a flow field surrounding it, right. So, when there is a relative motion between this droplet and the flow field, that is very important, because as you know, relative velocity also leads to droplet drag. So, that means you develop friction at the droplet surface. It also leads to internal recirculation, that means the liquid inside the droplet will also start to show some motion, and this will also affect, and this droplet is actually evaporating droplet. So, you can actually have the gasification effect that I said to you just a few moments ago, that the blowing effect, okay, that will be also part of this. Okay. So, we have to look all these things in a kind of a holistic manner if you have to kind of understand this problem from a very at different levels. So, there are models, there are very complicated models, there are very simple models also, which tries to attack this problem in a multitude of ways. So, this problem is not very different from a sessile droplet, except that there is no substrate over here anymore, right. But the mechanism of evaporation as it is shown over here is still the same. Okay. Now, if you do not have a flow, the diffusion or the J flux is also the same, except that J over here, that means the evaporative flux over here then will be isotropic, that means it will be the same everywhere, because there is no substrate effect at all, right. However, when you actually have a flow that happens over the droplet, this evaporative flux will start to change, right, because of the because when you actually have a flow over a droplet is like flow over a cylinder, right. So, you can have wake regions that can actually develop, and then you can have complicated motions within the droplet. So, the situation will be a little bit different. So, what we are going to do in the immediate lecture that follows is basically we are going to look at a couple of these problems from a very heuristic point of view, so that you get an idea that how to attack these problems, okay, in a multi-phase system. Okay. This is strictly not a multi-phase flow class, this is just to give you some bird's eye view about what are the different multi-phase problems, typical multi-phase problems involving droplets can be. Thank you.